we can get started. So we finished last class. We wrote down the Kantorovich problem, and we proved that actually it does have a minimum under some mild assumptions. So that's great. So we want to now study this formulation a little bit more and see what else we can draw out of it. What else can we learn about solutions to the optimal transport problem? So I'm going to start by looking at the discrete case when we have Dirac measures. And then, there's sort of finitely many places that you're allowed mass to go. So, you're effectively doing a finite dimensional problem at this point, and it's maybe a little easier to see a bit of the structure that's going on. So let's start here. Can you read that, pen? It feels like it's fading.
No, it's not visible.
It's not visible. Okay. You guys need to tell me when the pen starts to become invisible, because I'm standing like this close to it and I can still see it long after it becomes invisible to all of you. That looks better. Okay, so let's consider the discrete problem. Okay, so what is the discrete case? We've got a measure that I can write as finite sum of Diracs. So I'm going to write this as ui times delta xi. Okay, so ui is the amount of mass assigned to each Dirac. And similarly, my target is going to be a sum of Diracs, not necessarily the same amount of Diracs. Right? If we were doing the Monge problem, we definitely need them to be the same amount because we can't split mass around. But in the Kantorovich formulation, it's fine if the number of mines, say, was different from the number of factories. Okay, so my target is going to be also a finite sum of Diracs. Okay, so this is effectively finite dimensional. Okay, we're, as before, going to be looking for this measure pi, right, that tells us what our transport plan is. So pi is also going to look finite dimensional. Pi is also finite dimensional. And what does this mean? This means that I need to index it by all these i's and by all these j's, right? And pi ij is going to tell us how much mass moved from xi to yj. Yes? Okay, so this tells us how much mass moves from xi to yj. Okay, so we want pi. We have constraints on it, right? We have constraints that the marginals are correct. So our constraints are that pi at any set, let's say at pi x over the entire target set y, right, should just look like our original source. Okay, and also, the other way around, over the whole set x at any point y, we should get back our target measure. Okay, but now we can write this in terms of these u's and v's, these weights. Okay, so what does this mean? This means that here we're integrating away the y dependence. So if we integrate away the y dependence, we're going to add up over all our target masses, okay, of pi ij right? This should now just give us back our source measure. Right, our source measure, which is this guy. And if we integrate away the x dependence, we should get it back our target measure. Okay, and then one more condition that we might want to put here. So we're trying to make things as discrete as possible. So here we have these assumptions that pi is some kind of probability measure or some kind of positive measure. Here we've got the right marginals. If we want to make sure this actually looks like a positive measure, we should also include the constraint positivity. Right, because that's not automatic from just having the right marginals. Okay, so these are our new constraints. And we have an objective function. Our objective function is going to look like, okay, before it was we're integrating over our product space. So that looks like a double sum now. I equals 1 to n, j equals 1 to m. Okay, of the cost of moving from xi to yj, so that's, I'm going to call Cij. Okay, and this isn't an unknown. This is something we can compute because we're given where all the xi's are and where all the yj's are. And then times pi ij. Okay, so what is our optimization problem? Our discrete optimization problem now is, I'm just going to write this all together. Okay, so minimize this objective function, subject to. Okay, again, I'm just writing down what's already there. We've got a couple equality constraints. And we've got an inequality constraint. Okay, this is going to be for I equals 1 to n, j equals 1 to m, and this is over all possible values of I and j. All right, what can you tell me about this optimization problem? It's linear, yeah. This is a linear program, right? So some of you, those of you who have taken COMEX optimization should recognize this. If you haven't, that's okay, right? All right, so our unknown here is pi, right? And pi, you can think of this unknown as a vector. It's just a list of discrete values running through all the i's and j's. Okay, this objective function that we're trying to minimize is linear in the pi ij's. We have some equality constraints, but these are also linear in the pi ij's, linear in the pi ij's. And then we have an inequality constraint, which is also linear in these pi ij's. Okay, so this is indeed a linear program. Which feels like a really nice simplification from the original problem that we started with, you looked at the original same-Walsh problem, which just looks wildly nonlinear. This is quite clean and simple. Not to say that it's easy to solve it efficiently necessarily, but it's nice and clean and we know a lot about it. One thing that we know about linear programs is that we can write down a dual formulation of the problem. So the dual formulation is just going to be a new optimization problem which essentially is going to try to exchange the role of your objective function and your constraints, more or less. It's going to have a new solution, which is not the same solution as this. What it will give you is some information about the optimal value of this guy. So typically, here we're having a minimization. When we do the dual problem, we'll be maximizing something, and the maximum value of that is going to be a lower bound for the minimum value of this. That's called weak duality, and if you're lucky, which we are in this case, actually the optimal values are the same. So we'll certainly learn something about the optimal value of this from the dual problem, and we may be able to learn a lot more. Sometimes it will turn out when we do this for our optimal transport problems, the dual problem, if we can solve it, is going to let us construct solutions to the problem that we really care about. Okay, so let's talk about the dual problem. So linear programs have a dual problem. Okay, I'm going to write the general form first of all, for those of you who haven't seen it. By the way, a really good reference for optimization, if you haven't studied it before, is Boyd's book on convex optimization, and on Canvas I've posted a link to it. It's available free online. But you don't have to become experts in that. Okay, so we have a dual problem. So the original, the primal problem, is something like this. Let's say we want to minimize something like B transpose Y. Okay, so B is a given vector, Y is the thing that we're trying to come up with. Subject to, A transpose Y is equal to some C, and Y is greater than or equal to 0. Okay, so this is a general form of a linear program that matches the form that we've got here. Right? We have something that we're trying to minimize, so our unknown dotted with some given values, that's what's going on here. Some equality constraints that are linear in our unknown. Here, they're linear in our unknown. And then a positivity constraint. Okay, the dual problem for this is going to be a maximization problem. Maximize C transpose X. Okay, so this guy here that was sitting in the equality constraint now shows up in the objective function, and subject to AX is less than or equal to B. Okay, and similarly, this guy here that was sitting in the objective function now shows up in the constraints. What's that? When I say AX is less than or equal to B, this is going to be, okay, because it's vectors, yeah, this is going to be pointwise. Yeah, good question. So, or component-wise. So AX is a vector, and B is a vector, and the components we can compare. Okay, so let's see if we can do this with our problem. Yes?
Is it obvious?
Is it obvious?
That the dual problem yields a solution to the primal problem?
I don't claim that it yields a solution to the primal problem. What I will claim, and we're going to actually show this for the optimal transportation problem, is that the value of this, the value of this is a lower bound for the value of this.
Okay.
So it's not, I'm not saying that X and Y are going to be the same. They're not. We don't expect them to. They are not necessarily the same size of object even.
Okay, let me rephrase the question. I wouldn't have thought to write that down. Is there some intuition as to why we're looking at that in Boyd's book?
Boyd's book, let's see, will I have any intuition?
Or does he just claim that this is what we're going to do?
He probably claims that this is what we're going to do. So what I am going to do, we're actually going to do an exercise for the optimal transportation problem where in a like two-line proof, we actually find out that this is less than or equal to this. So we'll be able to kind of see how this pops up naturally. So if you give me a few minutes, for the problem we actually care about, I'm actually going to prove it to you in more detail than this. But you should be able to, if you want some intuition a little bit, is to just take this thing and dot it with x, which is this dotted with x, right? And you can jump back, then you pull out this constraint and jump around like that, and you can sort of get these bounds out. So the dual formulation for our problem is, okay, so what do we need? We have a new maximization problem. So what's playing the role of C here? C is the right-hand side of our constraints. So that's all the values of our source measure and also all the values of our target measure. Okay, so that means I'm going to be adding up this times an unknown and adding up all of these times an unknown. So I'm going to need a set of unknowns to go along with each of them. So I'm going to bring along what I'm going to call u's to go with these and v's to go with these. So those are going to play the role of my y's. Okay, so here, the role of y is going to be played by u1 to un and v1 to vm. Now, what do we want to do? We want to maximize I equals 1 to n ui times mu I plus j equals 1 to m vj nu j. Okay, so this is my new objective function. And again, these are totally different variables, right, than the pi's. They're completely, this unknown is a completely different size than the pi's that I started with, right? Because the original pi I started with has n times m unknowns, and this has n plus m unknowns on it. So it's a different beast. Okay, and then we're going to have some constraints. What were our constraints? Our constraint was an inequality condition, ax less than or equal to b, where a somehow shows up in our equality constraints here. And here, we're just adding up. A is trying to just add up everything. Okay, so again, we're going to be just adding up everything. ui plus vj is less than or equal to b. Where was b? B showed up in the objective function. The coefficient that came in the objective function were theseCij's, the cost function. So this is Cij. Okay, and again, as was pointed out, this is component-wise. So we've got to do this for all values of I and j. Yes? Where are you looking at? The role of, oh, I just mean, you're right, it's the role of x. The role of x, thanks. Yeah, so the role of y was played by these pi ij's. Okay, so this is our new dual problem. I guess one immediate advantage is that the unknown looks a lot smaller than the unknown that we started with. On the flip side, we have a lot of constraints here. But in some sense, this is giving us two sides of the same problem, and one may be easier to solve than the other. What I claim here, and I'm going to argue this in more detail, that we have this dual problem. The maximum value of the dual problem is equal to the min of the primal problem. cost function in the dual problem? Sorry, which part? You mean this thing here?
Yeah, it's in general. Is it really general?
The Legendre differential transform is going to show up either at the end of today or the beginning of next class. It's actually absolutely critical in a lot of these problems. So yes. So we'll end up starting either the end of today or next class. We're going to take a little pause to review a bunch of convex analysis because we cannot study this stuff without knowing some convex analysis. So right now this is just the cost function, but taking Legendre transforms is going to let us use this stuff. Okay, so this was the discrete problem, right? I wrote it down at the discrete level because when you write it down at the discrete level, we were kind of immediately able to look at this and say, oh, this is a linear program. We've seen these before. We know things about them. We know there's a dual problem. We know there's duality results that can let us do this. Now my question is, we might be interested in studying discrete optimal transport, or we might be interested in studying continuous or semi-discrete optimal transportation. Can we write down a similar dual problem at the more general level, which if we do, we can't just immediately take advantage over everything that's known about linear programs like this, but maybe a lot of these results still somehow go through and can be used to learn about our optimal transportation problem. So this is what we want to do. We want to say, this is great. This is the discrete problem. Now how do we generalize this if mu and nu are more general measures? Can we write down something like this? Okay, for more general measures. So what I'm going to do, I'm going to start by saying what's the most obvious dumb way to try to generalize this. And I'm going to write down that problem and say, let's just study this problem. Upon first writing it down, we can't claim that it's a useful thing, but if we study it, hopefully we can start to come up with some connections to the problem that we really care about, the Kantorovich problem. So I'm going to propose to do this. Let's propose to study. Okay, again, I want to make it look like this, so let's maximize something. Okay, because it was discrete, we had a sum here. That's obviously going to turn into an integral of some, now instead of discrete object, some function against our measure. Some function against our measure. All right, so let's integrate over our source domain, u of x d mu of x, plus, and an integral over our target, v of y d nu of y. Okay, subject to a constraint. So here the constraint was that at any point, pick any point xi, pick any point yj, the sum of u and v is less than the cost function between them. So the natural way to generalize that is to say u of x plus v of y is less than or equal to the cost of moving from x to y for all xy that live in the appropriate sets. This is a reasonable generalization. Okay, again, I haven't claimed at this point that this is useful at all. It's just I wrote down a problem which may or may not have a solution. It may or may not have anything to do with optimal transport, but hopefully it has something to do with it. I'm going to write down some shorthand for my constraint set. I'm going to call it capital Phi. And this is going to be the set of all u and v. Let's say that are continuous functions. And that satisfy this constraint. So such that u of x plus v of y is always less than or equal to c of xy. I'm also going to give this guy here a name. I'm going to call this thing j of uv. Okay, and for reference later on, I'm going to let I denote the objective function from my original Kantorovich problem. So this is the integral of my cost function against the measure pi. Yeah, it's just for shorthand. Okay, so one thing I claimed is that we're hoping that the value of this, that I'm trying to maximize, the objective function for my dual problem, provides a bound on the optimal value from my primal problem. Okay, so let's check. Let's make this observation. Okay, so let's just start with this thing, j of uv, which we wrote down. I would like to somehow get this related to something like this, which means I need to turn this into an integral over the product space somehow. How can I do that? I can use the marginal values, exactly. There's a known relationship between this mu and this pi, as long as pi is feasible. So we know that if I integrate over the product space, right, and I have something here that just depends on x, which is what I have here, right? I just integrate away the y dependence, and I come back to this measure that I cared about. So this is nothing but u of x d pi, right? Again, the y, I integrate away all the y dependence and get back here, and same deal here. This is v of y d pi. Okay, so this is just me writing down the objective function and feeding in the constraints that I had. Right, which is what I suggested here. You could write down the objective value, objective function, and then start feeding in the constraints to try to get a relationship between these things. Okay, let's see what else we can do. If I put these all under one integral. Okay, again, I'm going to keep doing the same thing. Let's feed in the constraints that we have. So here I fed in the constraints on the marginal from my primal problem. Now I can feed in the constraints from my dual problem, right, which says that this sum had better be less than the cost function. So this is c of xy d pi. Okay, and that is precisely the value of the objective function coming from our primal problem, coming from our Kantorovich problem. Yes, we believe this? Okay, so that means if I study the dual problem, at the very least, I'm going to get some bounds on sort of my total transportation cost. Now, we'd love to do a little better than that and say, can we actually get an equal sign here? So this right now, this is weak duality. Now my question is, can we make this tight? So this holds, if you put any feasible u and v in here and any feasible pi in here, this inequality always is going to hold. And what we want to know is, if I happen to put the optimal u and v in here and the optimal pi in here, could I make this inequality? So could we get equality using optimal values of u, v, and pi? Okay, I'm going to start by convincing you at least that this is reasonable, if not giving a fully rigorous result. For full rigor here, we still need more tools from convex analysis. So I'm going to give you most of it, and there's going to be one step where we put a question mark and say, this looks like it's probably, hopefully, a reasonable thing to do, but we're not sure until we learn a little more convex analysis. So let us see what we can do. Let's start with one side of the equation. So before we started with this and we got the inequality this way, now let's start the other way. So let's look at the infimum over feasible pi's. Again, this is not going to be equal for any choice of pi, any choice of u and v. We're just hoping to get equality for the optimal values. So the optimal values come when we're minimizing this or getting the infimum of this. Okay, so this, I'm going to use a trick. So the trick is that I have this complicated constraint now on pi's measures that have the right marginals. Instead of having a problem with this constraint, I want to somehow build the constraint directly into my objective function and say, as long as I minimize this objective function, the constraint's just automatically satisfied. Which, you know, if you've seen like barrier type methods, you see something like this done. Okay, so now I'm not assuming that pi lives in the set. It's just some sort of positive measure. Okay, I'm going to have I of pi here. And now I'm going to just do something really simple and dumb. I'm going to say, as long as the pi happens to be feasible, I'm going to add nothing to this. I'm just going to be happy. If the pi happens to be infeasible, then I'm not happy. I don't want that to give me the value of my infimum, so I'm going to penalize it really hard, and I'm going to say, I'm going to add infinity to you anytime you try to give me an infeasible value. And infinity is not going to give me the infimum. Okay, so I'm going to add this new function, 0 if pi is feasible, and plus infinity otherwise. Okay, so the value of the infimum hasn't changed, and we're guaranteed when we minimize this that our minimizer, if a minimizer exists, our minimizer has to live in the feasible set. Because anything doesn't live in the feasible set automatically gives us the value of infinity. Okay, so that was a simple dumb function that I wrote down. And now I want to try to write that simple dumb function in a more clever way that lets me somehow feed in the dual problem. All right, because we're trying to somehow relate this to our dual formulation, to this guy here that I called capital J. So here's what I'm going to propose. We've got, again, the infimum of overall pi that are positive measures of I of pi plus well, I said I want to feed this in, so let's just write this down. this on its own is presumably not equal to this funny function. But let's just write it down and then see what we need to sort of add or subtract from it to help us arrive at this funny function. Okay, I leave a little gap here for a moment. Okay, so I'm going to have u d mu plus v d mu okay, now I've got to, this is not expected to be 0, certainly. I want to subtract off something so that this whole thing is equal to 0 if we're in our feasible set. So an obvious thing to do is to use a trick that we've already used before and to take advantage of, if we're in our feasible set, we have the right marginals, right? If we have the right marginals, then I could rewrite this combined as an integral over the product space. So x cross y of u of x plus v of y times d pi. Okay, if pi is feasible, right, we said if pi is feasible, we've got the correct marginals here, then we're going to recover here a d mu and here a d nu, and this whole thing is 0, which is what we want. Now, what we also need is that if pi is infeasible, this had better give us infinity. I have choices here, all right? I've just introduced this u and this v, but I haven't said what they are, right? So we just have to pick something. So let's pick something. Let's see if we can pick the u and v that make this whole expression as large as possible, right? You know, we're trying to get something that could potentially hit infinity. So let's start by saying, well, how big can we make this? And I'm going to just say, let's let this be the supremum over all u and v. I think I'm missing a closing brace there. Okay, again, if pi is feasible, it doesn't matter what u and v I've chosen. The marginals are correct, and this gives me 0. If pi is feasible, the marginals are not correct, and I'm going to get something non-zero in here, right? So then I say, okay, maybe I did this, and it equaled 1, say, just for the sake of argument. Well, that was with a particular choice of u and v. Now I'll do the same thing but I'll replace u by 2 times u and v by 2 times v. All of a sudden I've doubled the value. Or replace it by 1,000 times u, 1,000 times v. I've brought the value up by 1,000 times, and I can make this value now as large as I want just by taking a u and v and rescaling them. So this whole thing I claim is unbounded if we don't have the correct marginals. We believe that? It doesn't have to be positive. Okay. Why don't I take this on a separate line? So let's just do a little interlude here. Why does this work? Okay, so let's suppose that pi doesn't have the correct marginals. Okay, then we can certainly find functions u and v such that this function, u of x, d mu of x, plus v of y, d nu of y, minus all of this, pi, is not 0. Do you believe that step? Right? If we always got 0 here, no matter what choice of u and v I put in, then I would have to say, well, the marginals must be correct. Right? Okay, so I say, now let's take that u and v. And in fact, instead of saying not equal to 0, I'll put something in between here. This is equal to some value k, which is not equal to 0. And then I can, yes. So then I can say, well then, let's just put in, say, plus or minus m times u, plus or minus m times v, and use linearity. Then inputting, say, plus or minus m times u and plus or minus m times v, I can get a value of plus or minus m times k, right? Which I can make arbitrarily large. Okay, and that means the supremum is infinite. Okay, and that's what we want. If we've got an infeasible pi, the supremum is infinite. That's what we wanted. That was the thing that says, no, we don't like infeasible pies. If pi is feasible, then it doesn't matter what u and v I choose. The marginals are correct. This thing is always 0, which again is what we want. Okay, so just to recall what we have here, we have the infimum of our primal problem. Okay, which we said is equal to all of this. I'm just going to pull the soup out all in front. Right, this guy doesn't depend on u or v, so I can pull the soup in front of him. Inf overall pi and the soup overall u and v of everything that we've got in there. I of pi plus. Okay, we integrate over x, u of x d mu. We integrate over y of v of y d mu. And subtract off the integral over the product space. Okay, so far, hopefully there's no problems with doing this, right? Well, the good thing that we've done is taken the optimal value of our primal problem. We've related it to something that at least now involves the objective function from our dual problem, which is good. Now what we want to really do is relate this value to the maximal value of our dual problem. Right now I've got an infimum out in front. What I really want is a supremum of u and v out in front, because at the end of the day, we want something that looks like the supremum of u v of j. That's the dual problem. So this is the sketchy step. The sketchy step is for me to say, here I have an inf and soup. Can I switch these around, right, and do a soup inf instead? So this, I'm going to put a huge question mark under, because this certainly doesn't have to work. Can I swap these things? Of all of this stuff. I'm not going to write it all. Okay. It's not totally unreasonable that this might work, but it's not obvious that this would work. But let's just sort of hope for the moment that it works and just see what happens. Does that get us anywhere? Okay, so what is going to happen here? Let's see. Now, again, I'm going to, okay, here's the part that we really want, right? That's our objective function that we're hoping to turn this into, yeah.
Did we make any assumptions on the space big pi?
Did we make any assumptions on the space big pi? So remember when big pi was the space of probability measures that have the correct marginals. When I'm sitting here, I'm not assuming that pi belongs to big pi I'm just assuming that it's a positive measure, right? And instead, the constraint was built into all of this mess here. So here, we're not assuming that constraint. Here we are assuming the constraint. Why are positive measures necessary? Because, let's see. So it probably wasn't strictly necessary for, this, but it doesn't hurt us here either, and it will make the next steps easier to do. Okay, so let's see what happens when we swap these things. We've got, if this worked, we've got a supremum over all u and v of, okay, this is the part that I really want, and it doesn't depend on pi, so I can sort of move the infimum of pi inside of this. So u d mu d mu. I guess we do need the assumption it's positive measures here, because reformulating it like this just use the assumption that we have the right marginals, right? But it doesn't really tell us anything about pi being a probability measure or a positive measure. Okay, so we have this u and this v, and then we have everything that's left over. Everything that's left over also includes pi. So we've got to hang on to this infimum over all pi. Okay, of I of pi plus, let me actually write it down what this is. C of xy d pi minus u of x plus v of y d pi. Okay, so what I want is for this to be equal to the supremum over u of v of all of this, subject to u and v satisfying some appropriate constraints, right? What I currently have is the supremum of u of v over all of this, and the constraints don't really live here, or do they? Remember, our constraints are something like u plus v is less than or equal to c, right? Everything that should belong in our constraint is somehow here. So maybe what we hope is that we can do this trick again, but now with this constraint. Okay, so let's see. Let's look at this. So let's suppose u plus v is less than or equal to c everywhere. Sure, yeah. We are assuming that we're living in the space of continuous functions, though, here, right? So I started by saying u and v are continuous functions. And last class, we made an assumption that c is continuous. So almost everywhere is going to become everywhere. Okay, so let's see what happens here. If u plus v is less than c, then what happens? So that means that this integral here well, this is always positive or 0, right? What's that? And now we need that it's a positive measure, exactly. And we're going to say, well, what's the infimum of this thing? The infimum is 0, exactly, right? So here, we're not assuming pi has the right marginals. We're not assuming that it's a probability, that it has total mass 1 or anything like this, right? It's just some measure, some positive measure. And that means that we can pick a positive measure that gets this value arbitrarily close to 0. So you can say the infimum is 0 since pi is a positive measure. Okay, so if we live in the constraint set, this infimum is equal to 0. That sort of matches what we did over here, where we had said if we live in the constraint set, this supremum was equal to 0. Okay, what if we don't live in the constraint set? Now let's suppose u of x plus, say, v of y star is strictly greater than c of x star y star. Okay, that means at some point this integrand here is negative. Okay, and now we want to find the infimum of this thing. Okay, so what's the infimum of that over all positive measures? Negative infinity, yeah. So for example, I could stick a delta measure here at this point, right, and put a big weight in front of it that gets arbitrarily large. So for example, say pi is equal to some constant m times a delta at x star, y star. Okay, then taking m to infinity, this value here becomes arbitrarily negative. This guy here right? Because by putting in this delta measure, I'm just picking out the one value where this thing was negative, and then multiplying that negative number by something that's huge. Okay, so if we don't happen to live in the constraint set, this infimum here is going to be minus infinity. So the infimum is minus infinity. Okay, so what have we done? We've taken this infimum here, and we've said there's two things that can happen to it. There's only two values it can have. If we live in our constraint set, this infimum is 0. If we don't live in our constraint set, the infimum is minus infinity. Okay, so if we go back to our problem, that means that the thing we started with on the left-hand side is equal to, now we come to here, we have the supremum over all u and v that are continuous functions of, okay, we have all of this here. In fact, I don't even have to write all of that. This I simply called j.
Sorry, the infimum of pi, right?
The infimum of pi.
But what is it?
Yes. Yeah, thanks. Okay, so this part here was my j. That was the objective function for my dual problem. this thing here was the thing that was either 0 or minus infinity. So this is 0 if u and v belong to my constraint set, and it's minus infinity otherwise. Okay, so if we happen to live outside of our constraint set, this gives us a value of minus infinity. We're trying to maximize things here. That isn't what we want, right? So if we're trying to maximize or compute the supremum here, we're automatically going to be forced to have something in our constraint set that lets us have a value that's either finite or possibly infinity if this would happen to blow up on us. Right? So automatically, this does, in reverse, exactly what we did here is say, we can kill this and say this is equivalent to having to live in our constraint set. So this is exactly equivalent to saying the supremum for uv in our constraint set of j of uv. Right, so what does this say? There's a relationship between the primal and the dual problem. We wrote down the Kantorovich problem, and then we wrote down some other optimization problem, which, okay, it used some of the same objects from the original problem, but it's a completely different optimization problem. And now this suggests, okay, we don't prove because I had a one sketchy step here, but this suggests that there's probably a relationship between them. It's reasonable to suppose there may be a close relationship between them, that actually the optimal values of these things are the same. Okay, so it's reasonable, we hope, maybe, to suppose that there's no duality gap. Okay, the minimum of the primal problem equals the supremum of the dual problem. Okay, so for now, I'm going to say, you can look in Villani. It's in section 1.1.6 on page 23 for the minimax principle. That allows this. It relies on tools from convex analysis, including the Legendre transform, which is indeed extremely important here. So before I go on, is there any questions on this result or pseudo-result? Yeah.
So, the problem is trying to find this sort of cost function.
The dual problem is trying to find the supremum of some sort of cost function.
But do we know, in that formulation, do we know the measure
So mu and nu are our given data, right? So we're given an optimal transport problem. Mu is our source, nu is our target, and those are always given data. Now, when we solve the dual problem, we're solving it with those same data, with the same cost function. Just these new unknowns, u and v, which we're going to see in a little bit. Are those u and v useful? What do they tell us? How do they relate to what we care about?
I was a little bit confused because I saw that mu and mu was part of the original problem.
Yeah, mu and nu are part of the original problem, exactly.
So you're trying to find a map between them.
That's right. Yeah. So from trying to find a map between them, we relaxed it and said, well, let's not find a map, let's find a transport plan. That's we called pi. And then we said, now let's write down a new optimization problem, the dual problem, where we try to find u and v. Okay, it's not clear yet how u and v are related to pi. It turns out they are, which we'll see. But it's all related, and it's the same data. Yes?
Does Villani take care of that question mark right there?
Villani fills in the question mark in that section. It's not that long. What's that? You can take the negative and do both of them in phelum, and then you still have to make an argument that this is allowed. Okay, so it's clear, hopefully at this point, that we can't, there's only so far we can go without knowing some convex analysis. So I'm not going to do an exhaustive study on convex analysis, but I want to make sure we have some basic concepts in place about what are convex functions, what is the Legendre transform, certainly, that's important. How can we generalize, what kind of differentiability do we expect in convex functions? We need that to go farther. So I'm going to put the Kantor-Ovich problem on pause for a little bit, and let's just fill in some background that we need so that we can keep running with this and learn a little bit more. I will also say that when we come back to this, I'm going to be assuming that we're working with quadratic cost. I think later I'm going to also show a little bit about how to generalize to non-quadratic cost, which it turns you need to generalize the notion of convexity somehow, generalize your concept of derivatives and subderivatives a little bit, and there's ways to do it. But let's start with things where we hopefully have a little bit of intuition, because it's a lot harder to build intuition for the non-quadratic cost. Okay, so we're going to, for now, we work with quadratic cost. And really very little has been done, even in the literature, for non-quadratic cost, because it's just harder. Okay, so c of xy is equal to 1/2 x minus y squared. And we need some tools from convex analysis. Okay, I think last class or the class before we asked what is a convex function, so you know what that is, hopefully. I'll just quickly write down a couple definitions that are hopefully not too forward. So a set is convex if whenever you take 2 points in the set, you draw a line segment connecting them, and that line segment also lives in the set. Okay, so lambda x plus 1 minus lambda y should also belong to E. Okay, and we have notion of a convex function, which we talked about 1 or 2 classes ago, a function f defined on a convex set. Okay, is itself convex if for every x and y in the domain and lambda between 0 and 1. And here we said the function lies below a secant line. So f at points in between x and y is sitting below the secant line connecting x and y. So lambda f of x plus 1 minus lambda f of y. Okay, here are some properties of convex functions. Okay, I'm not going to go through and prove everything and give you you can have whole classes on convex analysis and convex optimization. So I want to give you some of the keys at least. One is what kind of differentiability do we expect from convex functions? We know we can have an absolute value function that has a corner. It's not differentiable, but it is going to be Lipschitz continuous, and that we expect in general, that in the interior of the domain, convex functions are Lipschitz. Okay, so a convex function should be locally Lipschitz on the interior of its domain. Okay, not necessarily up to the boundary. You could have gradient blow up at the boundary, for example. You can actually have discontinuities at the boundary. So it's locally Lipschitz. It's not necessarily differentiable everywhere, but it's differentiable almost everywhere. So a convex function is differentiable almost everywhere. And at those other points, you still have some sort of differentiability going on there. Okay, in the interior. So let me take the absolute value function as an example. There's clearly, it's clearly not differentiable at the point, right? But if you just look from the right, okay, it's differentiable if you just come at it from this direction. You've got a one-sided derivative here, and you've got a one-sided derivative from this direction. So that you expect in general. So here I've just written down, a function on R. You expect one-sided derivatives everywhere. In higher dimension, what you expect is one-sided directional derivatives everywhere. So if I just start at a point, even if it's a corner, and I decide I'm going to go that way, if I just go that way, I can compute a directional derivative that way. If I want to look behind me, I might get a completely different result. But if I'm just going that way, I can get a directional derivative. Okay, so if mu is some direction, call it a unit direction. Okay, then we can compute the directional derivative. Of f in the direction mu is defined for x in the interior of the domain. Again, everything can break at the boundary. And we'll write that df by d mu is equal to, the usual thing. Limit as h goes to 0 of f of x plus h nu minus f of x divided by h. And the key difference here is, I need to modify this a little bit. We're only allowed to come at this thing from one side, right? So h is going to go to 0 from one side only. If f happens to be smooth enough, then we can say something about its Hessian. What do you expect from the Hessian of a convex function? Positive definite, or positive semi-definite. So if f is C2, then it's convex. If and only if the Hessian is positive semi-definite everywhere. Let's see, for all x. Okay, so this is a matrix, and I've written greater than or equal to 0. What I mean when I write a matrix is greater than or equal to 0 is that it's positive semi-definite. I'm probably going to use that notation again. Okay, we can do more generalization of the concept of differentiability. So I said, okay, we can come up with these one-sided directional derivatives. We can also generalize the notion of differentiability or of a gradient to what's called the subgradient. So we can generalize the gradient to the subgradient. Okay, so just if we think about this geometrically, here's a convex function. Let's suppose I want to know its derivative at some point. Geometrically, what is that derivative? It's the slope of a tangent line, yeah. It's not a trick question, right? So here I would say I want to know the derivative here, some point x. Derivative is just the slope of this tangent line. Now let's do it again, but for this function that has, say, a corner to it. Okay, a lot of these points, that's fine, I can draw tangent lines. If I get to this point, now I have options, right? For a convex function, we think of a tangent line as something that just touches it at one point and lies below it otherwise. Well, now I can do that with lots of different lines here. I could draw this line, which just touches the function at a point and lies below it otherwise. I could draw this line, which just touches it at a point but lies below it otherwise. Right? There's just lots of different ways I could do this. That I could draw something that feels like a tangent line, touches it at this point and lies below it otherwise. So this is what's going to give us what we call the subgradient of this function. So the subdifferential, okay, this is geometrically, consists of the slope of all the tangent lines to f, right? Which in this case, there might be a lot of them. So the subdifferential or the subgradient is not a real valued function or a function that has values in Rn. It's actually a set valued function. So it could just give you one value. Like right here, there's only one tangent line I could draw. There's only one slope I'm going to come up with. But right here, there's lots of different slopes I can come up with. Actually, there's infinitely many of them. So my subdifferential is going to give me a set that includes all these different values. Everything between this is -1 up to 1. Okay, so let's try to write down a more proper definition than just the picture definition. So we need to decide on the admissible slopes. Okay, so let P be such a slope, okay, for f at the point x, okay, so in other words, at the point x, I draw some kind of tangent line, some kind of line that kisses this function at a point and lies below it otherwise, and this line happens to have slope p. Now let's just write down the conditions. What do we expect? The tangent line is given by L of x equals, okay, f of x naught plus p dot x minus x naught, tangent line or tangent plane. So in general, this is going to be a tangent plane. Let's see, let's call this at the point x naught. And our requirement is that this should always lie below the function f, right? For convex function, we want these tangent planes to lie below f, right? Just kissing it at the point x naught. Okay, so we require L of x less than or equal to f of x for all x. Okay, and that is basically the definition of the subgradient. So the subgradient of f at a point x in the domain is, now again, it's a set, and it's this set. So we're going to write it, this is our notation. So it's the set of all slopes that make this work. So it's the set of all slopes such that f of y is greater than or equal to f of x plus p dot y minus x. Okay, so this is the slope, this is the equation of my tangent line with slope p passing through the point x. And now I'm comparing it to the value of f at any other point, and this should be true for all y. And again, this could be a set valued. It could have many values. It could have just one value. Maybe it could be empty. But this is how we're going to generalize the notion of the gradient. And we can also look at the subgradient over a set. Sometimes we'll need this. Okay, over a set. Say U is, we'll write it as a subgradient of U, and this is just, okay, we started, each one of these is a set, now this is just a union of all the sets. So this is going to be the union for all x in U of the subgradient of f at each of these x's. Right, so for this simple example here, for f of x equals the absolute value of x, the subgradient at 0 is going to consist of, well, the allowed slopes are everything between -1 and 1. Right, so this is a set. The subgradient, say at 1, is just going to be equal to now a singleton, and it matches the value of the derivative. Any questions on that? Okay, I'm running out of time, so I will leave you there. I'm going to do a little more with convex functions next time, and in particular, we need these Legendre transforms. And then once we have some of that built up, we get back to seeing what we can learn about the Kantorovich problem.